Okay, good. So let me see which pages until which page. Until page 28. So image filtering. So wait a second. So I want to say you the Do you hear me now? Okay. So you hear me now? You hear me? Can you hear me? If you can hear me, please send one. I don't know what is the problem today. Okay. So let me explain. So we do the correlation and convolution with the, so you hear me? Okay. We do the correlation and convolution in OpenC. We will filter 2D. Okay. Filter 2D. Filter 2D convolves an image with the kernel. The function applies an arbitrary linear filter to an image. In place operation is supported when the aperture is partially outside the image. the function interpolates outlier pixel values according to the specific border mode. This is important. The function that actually computes correlation, not the convolution. This is the formula. If we want to say what I explained in mathematics, then it is something like this. We have a kernel, we have our image, and then we do some multiplication, and then we add them up, we aggregate the results, then we put the result in the destination image at location X and Y. Okay, so filter 2D, the parameters that it takes, input image, output image, D depth is desired depth of the destination image. We can see the combination here. Kernel is convolution kernel or correlation kernel. It is a single channel floating point matrix. So it is the kernel should be single channel and floating point values. If you want to apply different kernels to different channels, split the image into separate color planes using a split and process them individually. So the anchor of the kernel that indicates the relative position of a filtered point within the kernel. The anchor should lie within the kernel. Default value -1 means that the anchor is at the kernel center. We have also delta. It is an optional value. If you provide it, it is added to the filtered pixels before storing them in destination. Also, we have border type. Border types are like this. So, as I told you before, for example, these are the pixels of an image, one row, A, B, C, D, E, F, G, H. They are the values of the pixels. One way to pad image is using border constant. For example, you put some I. I, for example, can be 0. We add 0 on the left, we add 0 on the right. We have another way, border replica, which is the padded pixels will be the same value as the first pixel. And here the last one is H, so the other pixels will be also H, the padded pixels. Another way is border reflect. So we reflect from here, we add the pixels that are added, their value will be like these values of the image, but in reflection. Also, the depth values can be these. We will see them in the book, okay? So now I try to explain filter 2D. Sorry. So I explain again, image filtering. In this section, we are going to tackle how to blur and sharpen images. I think you have sound now. Applying both several filters and custom-made kernels. Additionally, we will look at some common kernels that we can use to perform other image processing functionalities. Okay, Abdul Razak, I can't do anything. If they can't enter LMS, you should try again. Or you can send a message to support of the university support center. Okay? I can't do anything. Uh, OpenCV provides CV2 filter to the function in order to apply an arbitrary kernel to an image, convolving the image uh, with the previous kernel. How this function works, we should first build the kernel that we will use later. So let me explain things in a code. Smoothing techniques. So let me run spider. I'm waiting that the spider is running. Is run. Then I explain to you something using a spider. So smoothing techniques, yes. Oh, it's about histogram. So first I run this F5. These are the results. We have an original image. We filter it using CV2 filter 2D, using a 5 by 5 kernel, using a 10 by 10 kernel. If you look carefully, you see that it is blurred. You see, for example, here and here. You see, they are completely different. It is blurred now because we apply a blurring kernel to it. Also, it is the blurriness of this is less than the blurriness of this. Again, here you see it is blurred. It is blurred. It is blurred, but it is less than other. It uses Gaussian blur. I will explain. Where what? This is a bilateral filter. This is another bilateral filters. Okay, I will explain them. So here we read the image. Here we create the kernel for a smoothing. Kernel average 10, 10. It is some ones 10 by 10 over 100. Okay, so the kernel averaging 10 by 10. It composed of 100 values. Then we divide by 100 because we want that the sum of all pixels be 1. We have another averaging, it is 5 by 5. we put every pixel 0.04. The sum of them also is 1. Now we call filter 2D. This is the image. This is the depth of the destination, desired depth of the destination image. The -1, it means that the result should be same as source image. Okay. Now this is the curve averaging 5 by 5. So this value. So this matrix is used for filtering. Then the results are put in this variable. We call filter 2D again, but this time with averaging 10 by 10. And the results will be in a smooth image 2D, F2D 1010. The function blur, this function takes the source image and the size of the kernel. Okay, I explained it as well. I come back to the book, then I will come back again. So here it shows us how we apply the kernel to the source image. So we use filter 2D in this way. Now we have seen a way to apply an arbitrary kernel to an image. So we can change this kernel and the results will be different. In the previous example, an averaging kernel was created to smooth the image. There are other ways to perform image smoothing. Image smoothing, also known as image blurring, without having to create the kernel. Instead, some other parameters could be provided to the corresponding OpenCV function. In the smoothing techniques script, you can see the full code for the previous example and the next subsection. As previously mentioned, in the smoothing techniques.py script, you will see other common filtering techniques to perform a smoothing operation. The smoothing techniques are commonly used to reduce noise. So one of the benefits of smoothing is reducing noise. And additionally, these techniques can also be applied to reduce the pixelated effect in low resolution images. These techniques are commented as follows. You can see the output of the screenshot. So these are the results that I showed you. So we can use CV2 blur and CV2 box filter to perform an averaging by convolving the image with a kernel, which can be on in the case of box filter. So we have box filter and blur. Let me show you. Blur and box filter. So blur. The blur blurs an image using the normalized box filter. So we specify car size, then we will have a filter, a kernel, which is car size width by car size height. Look, note that car size actually is height, width For example, it can be 10 or 11, 11. Okay, so this is two values. It has two values. So when we say here, we 1 divide by car size width multiply by car size height. Okay, so always the kernel will be this for Blair. But for box filter, the kernel that we use is multiplied by alpha. If a parameter normalized is true, then the alpha will be this. So it's same as the left. But if the normalized is not true, it is false, alpha will be 1. Okay? It explained here. They simply take the average. It speaks about Blair and box filter. They simply take the average of all the pixels under the kernel area and replace the central element with this average. You can control the kernel size and the anchor kernel by default minus 1 minus 1, meaning that the anchor is located at the kernel center. When the normalized parameter, which is by default true, of box filter is equal to true, both functions perform the same operation. In this way, both functions smooth an image using the kernel as shown in the following expression. So in box filter and Blair, we don't specify the kernel, we just specify its size. The kernel will be this. In case of box filter, alpha will be this, the car size width by car size height. Otherwise, if normalized is not true, it will be 1. For Blair, alpha always is this. In other words, Blair always uses a normalized box filter as shown in the following code. So when we call Blair, we write image here, and this is the size of the kernel. For box filter, we say, for example, normalize to true or to false. Uh, each one that is suitable for us. So actually, these two lines have same results, equivalent results, because normalize is true here. When normalize is true, these two functions are same. Also, we have Gaussian blur, which blurs an image by using a Gaussian kernel. This kernel for Gaussian, who knows what is the Gaussian kernel? What is the Gaussian kernel? Anyone knows? Anyone knows what is the Gaussian kernel? If you don't know, please send 2. Okay. So Gaussian function in one dimension, if we just have x, it is like this. Okay, it has a mu, it has a sigma in its formula. For example, you see here we have, for example, the blue one. Which laws you mean? Difference between what? Actually, Gaussian filter is better. It has less side effect. Uh, we have a mu, we have sigma. For example, when sigma 2 is 0.2, it is this one. So I want just show you that the Gaussian in one dimension is like this. I just wanted to show you this, nothing more. But in two dimension, we have x and y, a Gaussian, a sigma x and a sigma y, a sigma x and a sigma y. I just wanted to show you this. Uh, you see, it in two dimension, it is like this function. In one dimension, it is like this. So we take some samples. So if we show by in image, the kernel will be like this. You see, for example, here is the pixel which is here. It has more intensity value, so it is lighter. When we go uh, in the when we are in the center, it is big. When we go far from the center, the value will be smaller. So the light is less. So let me come back here. We have Gaussian-Euler function. SRC is input image. The image can have any number of channels which are processed independently, but the depth should be one of these. 8U means it's 8 bits and unsigned. 16, it means 2 bytes, 16 bits, unsigned. S means signed. F means float. Output image of the same size and type as SRC. Of course, it is optional here. And then we have sigma x and sigma y. Gaussian kernel standard deviation in each direction, Gaussian kernel standard deviation in y direction. So we should, when we want to use Gaussian Euler, we should specify sigma x and sigma y. If we just specify sigma x, then sigma y is set to equal to sigma x. For example, if we put sigma y to 0, it is set to be equal to sigma x. If those sigmas are 0, if we put both of them 0, they are computed from car size width and car size height. We don't have mu here. We don't have mu here. Actually, mu is 0 for here. So You should know that we sample the continuous Gaussian because the formula that I showed you, they are for continuous. Now we want some values. Alpha and scam laws, I don't understand you. So anyway, so you should provide car size, which is kernel size, when you want to use Gaussian Belair. You should provide sigma x, which is a standard deviation in the x direction of the Gaussian kernel. Sigma y, you should provide it. It's a standard deviation in the y direction. In order to know which kernel has been applied, you can make use of get Gaussian kernel. Get Gaussian kernel let's see, get Gaussian kernel, it's not here. Get Gaussian kernel. It returns Gaussian filter coefficients. You provide cos size and sigma, and then it returns the Gaussian filter coefficients, if you like. So using Gaussian Belair is very easy. You send the image, you provide the size of the kernel, and you see here we put the sigma x0, and we didn't provide sigma y. So sigma x and sigma y are calculated based on car size. So in the script, you see we have Belair, we have box filter, we put its normalized parameter to true. We have Gaussian Belair. Also, we have median Belair. What is median Belair? Median Belair is another type of filter. Who knows what is the median? Do you know what is the median? What is it? No, the image is convolved. The image is correlated, or it's better that I say the image and the kernel are correlation. We do correlation between them. Okay, I explained to you. We put the kernel, the center of kernel to at location, then the corresponding values between image and kernel are multiplied, and then they will be summed up. Yes, we can kernel values. We have several waves. We can set them manually. Sometimes we can specify them. For example, when we say do Gaussian Belair, then the Gaussian Belair has a formula. We just say what should be the size or what should be the sigma x and sigma y. Then the kernel, the coefficients are calculated based on those parameters. Median, the median is the value separating the higher half from the lower half. For example, here you look, we have 1, 3, 3, 6, 7, 8, 9. we sorted these values, the median of these values is 6. Because actually the number of them is an odd numbers, but if the number of them is even, then when first we sort and then the average of two values in the middle. Between filtering, what do you mean? The filters do different things. Okay, when we specify a filter or a kernel, uh, depending on what we want to do, we specify the coefficients. So median Belair, we can use this also, median Belair, which blurs the image with a median kernel. This filter can be applied to reduce the salt and pepper noise. What is the salt and pepper noise? Sometimes we have salt and pepper noise in the image. Salt and pepper noise image. Salt and pepper noise it is a form of noise sometimes seen on images. It is also known as impulse noise. This noise can be caused by sharp and sudden disturbances in the image signals. For example, this image has salt and pepper. Some pixels will be white, some like salt. Some pixels will be zero, like so they are black. It's like pepper. Okay. So for reducing the salt and pepper noise, we should use median Belair function. So let me show you here. We use median Belair and image, and this is the kernel size. It is 9 by 9. So what is the bilateral? It is another filter that we can apply to an image. It also reduces noise while keeping the edge sharp. This is important. Normally, when we do filtering, for example, using Gaussian, using averaging, box filter, Belair, so the noise is reduced, but also the edge of the image also reduces. They are weakened. But if we use bilateral filter, it reduces noise while keeping the edge sharp. So for using bilateral, we specify image, and let me show you. Bilateral filter. It applies bilateral filter. It is explained here actually in this address. It can reduce unwanted noise very well while keeping it fairly sharp. However, it is very slow compared to most filters. We should specify d, diameter of each pixel, sigma color, and sigma space. So these are the sigma color and sigma space, and this is the size. Okay. Maybe we stop here, okay? So bilateral filter with a small size, this one with a larger value and larger values for sigma color and sigma space. So we in this script we read an image, we define some kernels, we filter image using these kernels by filter 2D. We use box filter. In box filter, we don't specify the kernel. We just say what is the size of the kernel because it normally uses the averaging filter. So if we want to use Gaussian Bel Air, then we can just specify the size, the sigma x and the sigma y of it will be calculated based on kernel sizes. Median Bel Air also it is a non-linear kernel. It doesn't convolution or correlation. It just when we say, for example, it is 9 by 9, the area of the image, the neighborhood of the image that is under the kernel, in that location, the values are sorted and the median of them is found and is put in the. So let me run it again. So you see, this is the original image filtered 2D with different values. Let me explain you something. For example, with Gaussian Bel Air, if I say 19 to 19, so we run it again. It is very more Bel Air now. You see, if I, for example, put, let's say 29, it is very messy. Still more, for example, 69. You see, it is more blurred, and its blurriness is a bit directional because the different values of the size in x and in y directions. So if I set them equal, you see, it is very blurred now. Still, I can increase that. Okay. So 9 by 9. I revert the changes. Rashid Mahdi asks which values of kernel are better, higher value or lower. It depends to what you want to do. Okay, you have no, and if you just want to raise, then the lower values are used. But if you want to remove a very powerful noise, you want to do some other calculations. For example, sometimes we blur an image with a kernel, then we subtract it from the original image for sharpening. Okay, so it depends to what we want to do. It depends to what we want to do. What is our purpose? So the kernels, the values, the coefficients in the kernels, and the size of them are calculated based on what we want to do. And I can't explain more at this step. I stop here. We see any question? No question? What do you mean? انتصار الفائلي. I didn't understand your question. We want to ask you whether we will take the entire source if we stop at a certain point. What do you mean? Maybe you mean entire score, no? الفائلي, I didn't understand what you mean. Oh, no, we stop. We don't say the whole book. It's for 2 3 semesters. Okay? No, we will stop soon. Okay? I think maybe we just say 1/3 of the book. No, 1/3, no. More than 1/3. Don't worry. So if you don't have any question, I stop here and I say goodbye to you. Goodbye.